Heat waves, drought, tornadoes, hurricanes, floods, blizzards, bitter cold. Extreme weather has an incredible impact on people across the globe. On Mount Washington, our scientists brave some of the worst weather on the planet to improve our understanding of our warming world. All right, good evening, everyone, and welcome to Mount Washington Observatory's Science in the Mountains lecture series with program support from MathWorks. My name is Brian Fitzgerald, and I'm the Director of Science and Education here at Mount Washington Observatory. And joining us this evening to discuss the science of fire weather is former Mount Washington Observatory weather observer and current assistant professor at the University of Nevada in Reno, and that is Dr. Neil Laro. Thanks so much for joining tonight's program. And for those of you who are not already familiar, the Mount Washington Observatory is a nonprofit member-supported organization whose mission is to advance the understanding of the forces that create Earth's weather and climate. And we accomplish that through operating our Summit Weather Station with around-the-clock weather observation and forecasting, by conducting research and product testing projects, and by developing and offering innovative educational programs. If you have questions for tonight's speaker and you're joining us through Zoom, please use the Q&A button that you can find at the bottom of your toolbar in the middle of your video screen. We're going to be able to collect your questions throughout the entire program, and we'll save some time at the end for a live Q&A session. So make sure you get your questions in whenever they come to you. If you're joining us on the live stream on Facebook, welcome and thanks so much for being with us. Our Summit staff will try and respond to some questions as they come in through that stream as well, though we may not be able to respond to those in real time for this program. If you'd like to connect through Zoom for the next program, please register using the program link on mountwashington.org/SITM. All right, and finally, if you aren't already aware, this Friday and Saturday marks the 21st annual Seek the Peak Fundraiser and Adventure Expo. This is the observatory's largest fundraiser of the year, which helps provide critical support for not only our operations, but also our ability to offer free programs just like Science of the Mountains. So if you are in the area this weekend, we'd strongly encourage you to check out seekthepeak.org. That's seekthepeak.org. You can sign up to participate in the fundraiser. You could also show up to this Saturday's Adventure Expo at the base of the Mount Washington Auto Road. You could always make a donation to support someone's who's participating in the fundraiser this year. And if all else fails, you can always donate to my personal page over at seekthepeak.org. You can just search Brian Fitzgerald's, hint, hint. Anyways, that being said, I think that's enough plugs for this evening. Let's get the program underway. And to kick things off, what we'll do is I'll launch a quick poll here. So everyone who's joining on Zoom, you should see a poll come up just about now. And we'll give you just a few moments to respond. So a few questions for you this evening. First, curious where you're joining us from, either the Northeast, the Mid-Atlantic, the Northwest, and maybe you're coming from the Southwest like our speaker this evening. We are curious, second question here, just out of curiosity, which ways do you typically interact with Mount Washington Observatory? I know a number of you come from a variety of different, joined with us in a variety of different ways. And so it may be through our weather data, maybe use our forecast all the time for hiking. Maybe you're joining an educational program just like you are now. Maybe you like our webcams. Maybe you're really into Seek the Peak. There are multiple answers that you can put down there. So any and all ways you interact with the observatory, just kind of curious here. And then a couple trivia questions from our speaker this evening. How tall do you think a pyrocumulonimbus cloud can get? 20, 30, 40, or 50,000 feet? And then we'll see if we can answer this one. This is actually a question that I had for our speaker ahead of time. I was curious, how frequently are pyro tornadoes, that is fire-generated tornadoes, observed? Is it once a month in the summer? Is it once a year, once a decade, once ever? I don't know. We'll hope to hear a little bit about that tonight. So just give you a few more moments. Looks like a number of you have already responded to the poll. And we'll end it in about 3, 2, 1. Alrighty, and we'll share some results with everyone. All right, overwhelmingly, the Northeast being represented, the one lone Southwest representative. I wonder if that's our speaker tonight. And we have one person from outside the country as well. Thank you so much for joining. All right, which ways do you typically interact with the observatory? Well, educational programs overwhelmingly led pretty closely there by the current weather conditions and also the higher summits forecast. And a good amount of you, 12 out of the 98 respondees, do interact with us through Seek the Peak, our hikeathon and adventure expo and fundraiser. Great. 30,000 feet was the winning selection. We'll see if that's how high our Pyrocumulus Clouds get. And then how frequently are pyro tornadoes observed? Once a month in summer. We'll see. We'll see about that. All right, we'll stop sharing the results there and let's get to tonight's speaker. Alrighty, so let's see. At this time, I'd love to welcome tonight's speaker, Dr. Neil Laro. Again, he's a assistant professor over at the University of Nevada in Reno. Neil, can you hear me okay?
I can, Brian. Can you hear me?
I can see you just great. Neil, why don't you take it away?
Okay, great. Well, thanks for the introduction, Brian. And it's real honor to be here talking to this group today. The observatory is actually where I really started my career in atmospheric science. I was a weather observer back in kind of 2004 to 2007 timeframe, starting out as an intern at the observatory, and has kind of launched a lifelong fascination with observing the extremes of the atmosphere, be those encountered at the top of Mount Washington, or as I'll show you, some of the extremes that we're looking at now inside of wildfires and the weather that they can produce. So yeah, really nice kind of full circle for me to be able to come back and give a talk like this to this audience. So thanks for the opportunity. I'm going to go ahead and start sharing my screen here. And oops. Okay, so yeah, the title of my talk today is just that: fire weather is extreme weather. When we think about extreme weather, we often think about tornadoes and hurricanes. And for those of you that follow the conditions on the summit, the conditions on high peaks and in mountain ranges. But fire can produce its own extreme weather, as we'll see in the talk today. And some of those extremes, in fact, rival some of the greatest extremes that we witness elsewhere in the atmosphere. And of course, you're adding to that mix the terrifying combination of things like extreme winds and combustion. So it's kind of like Sharknadoes, but with fire. It's a real thing. And of course, want to kind of acknowledge there's a number of people that contribute to some of the scientific work that I'm going to be showing here today. So my colleagues at San Jose State University and other universities around the Western United States, and also some of the funding for this comes from the National Science Foundation, as well as a program called the Fire and Smoke Model Evaluation Experiment. Okay, so a little bit of a disclaimer. I'm going to get pretty heavy into the science today, and my hope is that I can make it entertaining enough that you can parse some of that out and keep some of it with you moving forward from today. But some of this may get a little technical at times, but hopefully will remain interesting. So I always like to start these talks about what fire means to me and what my science is all about as a professor and as a researcher. And so the key question that I'm really interested in is, how does the atmosphere respond to fire fluxes of heat, moisture, and aerosol? And then kind of within that, under what conditions do fires generate tornado strength vortices and something that we call pyrocumulonimbus clouds? So that's all a bit of a mouthful, but if you kind of think about this cartoon over on the right, we have a fire that is emitting heat and moisture and aerosol. And that's what we see as these plumes coming off of the fire. And under the right conditions, oops, there we go. These plumes can grow deep enough that they get cold enough to actually trigger clouds that go on and kind of have a life of their own and can generate fire-generated thunderstorms, which is what we call pyrocumulonimbus. And what we'll see today is that when the ambient winds or fire-modified winds are sufficient, we can also develop very strong vortices within these, with winds up to about 140 miles an hour. So not Mount Washington winds here, but still some pretty impressive and pretty scary winds. I also like to talk about the tools that I use to accomplish my science. And my primary science tools are things like weather radars, Lidars, which are a laser scanning device that I'll describe in a little bit, and satellite observations that we can use to look at these. And so I have some pictures of those here on the bottom. And only half jokingly, another emerging scientific tool that I get to use is Twitter, which has proved to be a really remarkable tool for kind of crowdsourcing information about what's going on in wildfires. These are often occurring in complex, rapidly evolving environments, and there's really no central way to have information about what's going on in these. And so actually citizen science and kind of crowdsourced information has become extremely, extremely useful. All right, so let's talk a little about the science tools. Like I said, radar is one of the tools that we use to look at fire-generated weather. So weather radars emit pulses of electromagnetic radiation out into the atmosphere, and the characteristic wavelength for weather radars is somewhere between kind of millimeter wavelength and maybe like 10 centimeter wavelength radiation. And that goes out into the atmosphere and it bounces back, or a very small fraction of it bounces back off of particles suspended in the atmosphere. For example, raindrops are a great target for radars. Turns out wildfire plumes are also great targets for radars. There's all sorts of stuff being lofted inside of here. A lot of ash, for example, and the ash has kind of characteristic sizes, a lot like snowflakes, millimeter to centimeter scale. It tends to be kind of flat and fluttery. And so radars can actually allow us to look at the structure and evolution of these wildfire plumes. So here's an example of some very high resolution data from a rapidly scanning radar that we have. This is a deployable truck-based system that can go out to wildfires and scan around. And so this is an example from a prescribed fire out in Utah, where we can look in really intricate detail at the structure and evolution of these plumes. And really, this is kind of cutting edge stuff for us. We haven't been able to do this in the past. And the advent of some of these newer tools is allowing us to get a new look at what's going on in these environments. So that's one tool. The other tool is something called a Lidar, which is very similar to a radar, but instead of using long wavelengths, it uses actually infrared wavelengths, so just a little bit past the visible part of the light spectrum. And it sends laser beams out into the atmosphere, and those laser beams similarly bounce off of material and come back to the radar and allow us to, or Lidar, and allow us to kind of image what's going on there. So there's been some jokes in the media over the last few years about space lasers starting wildfires. And sometimes I like to describe to people that my job literally is to shoot lasers at fires, but that they're not space lasers, nor do they start the fires. So here's an example of what some of that Lidar imagery looks like. We can get some very fine resolution detail on the evolution of these smoke plumes as well, coming off of the fires. So my journey here kind of began on the very first fire that I went to, which is pictured here in this kind of jumpy time lapse. This is a fire on a military base in Central California called Fort Hunter Liggett. The name of the fire was the Stony Fire. And I had this scanning Lidar with me, and right in front of my eyes developed the very first fire whirl that I had seen. This was a strongly rotating anticyclonic vortex, and you can see on the right some of the Lidar snapshots that were taken through the base of this. And if you're a weather radar aficionado, you might recognize in this top panel what we call a velocity couplet. So this is, the blue is flow toward the Lidar, which is down here, and the red is flow away, and the vortex is right here in the center, and we're seeing the strong rotation associated with that here. In this case, this was probably about as strong as a very low-end F0 tornado, or something akin to a lot of dust devils that we get out here, especially in the western United States on hot, dry days out in the desert. So strong, but not particularly compelling in its impacts. And it turns out that fire whirls of all shapes and sizes are very common on wildfires. It's not an exaggeration to say that literally every fire that I've been to, I've probably been to 20 or 30 wildfires at this point, produces some form of vortex. And these can range in scale from very small transient whirls a few meters across to what I'll show you are full-scale tornadic circulations. And here are some graphical examples of the different morphologies that we see with these. And just generically, we call these things fire-generated vortices. They can take on all sorts of different shapes and sizes. Some of them contain flames, some don't. Some start in the fire and stay in the fire. Some start in the fire, and as you can see in this image here, actually shed off of the fire and move downwind from it, especially if there's a stronger crosswind. That's actually an example from the Burning Man experiment, or not experiment. Well, I guess there's a certain form of experimentation maybe that goes on there, but not the scientific kind. So it's a good example, the Burning Man case here of what I would call plumes in a crosswind, where the crosswind impacting the fire. Some other morphologies relate to fire geometry and what I'd call buoyant interactions, one part of the fire interacting with a different part of the fire and giving rise to these vortices. But really none of this adequately or fully explains some of the very large vortices that we see on these larger wildfires. So I'm going to jump now to what I would consider to be a full-scale fire-generated tornado, or a fancy term for that would be a pyrogenetic tornado, meaning a tornado generated from a wildfire. And this case pertains to a fire that occurred in 2018 in Northern California called the Carr Fire, which devastated parts of Northwest Redding on the 26th and 27th of July. This video here, which may be a little bit jumpy on your end, hopefully not, but shows an aerial view of this vortex. We have a cyclonic rotation here. It's about 1 kilometer in diameter. And as I'll show you, the winds in this case reached up to 140 miles an hour at the surface. You can see the tremendous impact of this on the flames at the surface, horizontal sheeting of flames flowing into this vortex. We have flames rocketing hundreds of meters into the air. And if you look closely, there are large pieces of burning debris being lofted as well, which can go on to cause spot fires. Some of the statistics for this, the maximum estimated wind speeds at the surface were the equivalent of an EF3 tornado, or 140 miles an hour. The vortex reached a depth of 15,000 feet in altitude. So the base of it was near sea level, and the top of it is at almost 15,000 feet, so higher than the highest peaks in the contiguous United States. The impacted area is shown up here in the top right. This occurred near the northern flank of the fire. And here are some of the examples of the damage that this did at the surface, wrapping steel pipes around trees, stripping roofs from houses, even outside of the area that is combusting, toppling high tension power lines, and tossing vehicles. And unfortunately, this actually contributed to 4 fatalities, including a firefighter who was working to evacuate one of the impacted communities right down here. And so the fatalities and injuries from this are shown on top of this. So these have a profound impact on life and property. This is kind of a radar overview of the tornado and where it was located inside of the plume. So the shading over here is showing the overall plume structure, which extends up to about, in this case, up to about 12 kilometers. Thanks. I got kids coming into the room. Bear with me for a moment. Thanks, Henry. All right. Thanks, bud. And the black line shows the location of the vortex within this plume. So it's embedded within the plume. And we can actually see the radar signature of the circulation associated with this. This was actually quite a ways from the radar site. What's interesting about having these observations is it allows us kind of for the first time to track the time evolution of what's going on in the environment here. And what I would argue in this case is that we have a kind of classic development similar to what we call non-mesocyclonic tornadoes. These would be like landspout tornadoes that you sometimes see in Colorado, where we have what I would call a shear zone. So a shear zone is a region of winds flowing in opposite directions separated by kind of a narrow space. And so the top image is here, some radar snapshots, and the blue is showing flow toward the radar and the red flow away from the radar. And we can see in the 30 minutes leading up to the vortex formation that we have a shear zone that broadens and intensifies in the magnitude of the shear. One way I like to think about that is similar to traffic flow on a highway, right? We have a median that's separating two oppositely directed currents. And so the region in between would be a region of high shear and a source for rotation. You could picture putting a paddle wheel in here, right? And it would spin. In this case, it would spin in this direction, a cyclonic sense of rotation. So that's kind of the antecedent conditions. But then something happens and we collapse within that shear zone into a distinct vortex, this strong rotation in a column that extends through great depth. And that's what we're seeing in those videos. And you can see then in these radar snapshots, these darker blues and reds emerging right next to one another. And that's this collapse of the shear zone into a coherent vortex. So why is that happening? Well, we have various math that tells us about this, but really it's similar to the analogy of a figure skater who starts with their arms spread wide in a weak sense of rotation. And as they draw their arms in, they have to conserve their angular momentum, and thus their rate of rotation goes up. And in the atmosphere, this typically happens when we stretch out a column of the air, which forces it to contract laterally as well. And so the stretching action in this case is being provided by the rapid growth of the plume. So that's going to stretch a column of air upward. And what that typically leads to is what we would call an exponential growth cycle. And that's what's shown down here on the bottom right. These line plots show the strength of the rotational winds in this vortex as a function of time. And we can see something that looks a lot like an exponential increase and then an exponential decrease in the strength of this vortex. So I would like to say exponential growth, great in your bank account, bad in vortices. You know, in this case, it's how you go from a relatively weak rotation to a tornado strength rotation in a very short order of time. What does that look like at the surface? Well, I find this video to be one of the most compelling. It's blocked a little bit by a windshield wiper here on a fire truck, but you can see the tremendous magnitude of the cyclonic rotation here. Again, as well as this huge inflow layer along the surface drawing air into the base of this vortex. And this is right near peak strength in here, up around 140 miles an hour for those rotational winds. And so you can imagine there's no way to fight fires that are producing this. It's everything you can do to get everybody out of the way of something like this. Okay, we still haven't answered the question for why did the plume get so deep so quickly? Why do we get such a tremendous stretching action? And so what's happening here is the generation of one of these PyroCB, which stands for Pyrocumulonimbus, or fire-generated thunderstorms. We get a nice view of this from a satellite image shown here on the left of the rapid vertical expansion of the plume as it moves upward. And the reason it's doing that is that as the plume grows, it reaches its condensation level, right? So it's 1,000 degrees down here, but it cools off as it ascends. And if it gets cold enough, it will condense the water in the plume, and it actually releases energy back into the plume as it does that. And so that's what we call releasing moist instability. It's really the same thing that happens inside an ordinary thunderstorm, only this is kind of supercharged because we have these huge fire-generated updrafts feeding the base of it. And so the top of that fire-generated thunderstorm in this case goes from about 6 kilometers in altitude up to about 12 kilometers in altitude, or up around 35 to 40,000 feet in altitude. So this is up around where commercial aircraft are at their cruising altitude. And the top of the cloud actually forms ice, and that's why we begin considering these to be fire-generated thunderstorms, because they're behaving very similarly to an ordinary thunderstorm. So it's really that moist instability release that gives us this very nonlinear rapid growth in the plume development. From some other fires, we know about some of the internal dynamics of these pyrocumulonimbus clouds. These are some of the most exciting observations that I've had a chance to work with. And what we're looking at here are radar images taken from an aircraft looking down into a developing pyrocumulonimbus. So we have 3 different time snapshots flying over a fire. The aircraft is up here and it's pointing its radar downward into the fire. And what's notable here is that these red and purple shades are flow upward toward the aircraft, and the blue are flowed downward. So let's just take a look at this image on the left. This is kind of like a slice or an MRI, if you will, of the plume structure. And it has a central updraft that's ascending through here, and it's flanked by these strong downdrafts along the edges of the plume. And if you look at what the maximum velocities are in here, these updrafts are around 130 miles per hour at an altitude of almost 5 kilometers. So this is where that profound stretching is coming from that can lead to the development of these vortices. And that stretching, these updrafts are stronger probably than has ever been documented, even in supercell thunderstorms over the plains. So we're really talking about some of the most extreme atmospheric convection outside of volcanoes that you can experience. Okay, back to the car fire. Now that was from a different fire, not the actual car fire, but it gives us some context. We can also see that there's a feedback between the generation of the vortex and the strength of the fire. And again, feedback cycles lead to things like exponential growth, which are not great in environments like this. And so the top is showing the growth of the cloud, and at the bottom, these are the kind of fire pixels from the satellite. And we can see right here, this very bright pixel showing up, that's right where the vortex is occurring. And it's leading to this rapid escalation in the rate of combustion, which then feeds back on the updraft, feeds back on the circulation. We get this exponential growth curve. So kind of putting this case all together, we have a wildfire developing in an ambient shear zone, which triggers a pyrocumulonimbus cloud, which leads to a vortex formation. And if you've ever watched the movie Twister, that's where you get cows flying around through the air, is once you get that vortex to collapse in that environment. And again, this is actually very similar to the way something called landspout tornadoes form. So these are not the monster supercell storms that produce the F5 tornadoes, but usually weaker tornadoes that pick up some sort of sense of rotation in the atmosphere and stretch it out. And in this case, the fire and the pyro-CB are providing that stretching. Okay, so that was kind of a very exciting scientific development for us, being able to understand that particular case and use radar data to probe it. And fast forward to last summer, and it seems like every year right now is kind of a one-upping of the previous years. We're off to a kind of scary start already for 2021. But looking back at last year, we actually wound up with 3 cases of full-fledged fire-generated tornadoes. And I'm going to highlight some of the dynamics that we've learned about those in the next sequence of slides. So what we're looking at here is a fire called the Loyalton Fire, which occurred actually just north of my house. So I live in Truckee, California, and you can see this from my house. There's a picture of it in the top right there. You can see this intense combustion and heavy smoke down here, smoke and ash, and then in the upper portion of development of this pyrocumulonimbus cloud. And what we're looking at in the animation is the radar, what I call isosurfaces, kind of the volume occupied by the plume. And we see these dark reds rocket upward and the plume go through this rapid development right in here. And that corresponds to the period that this fire produced fire-generated tornado strength vortices as well. So before I show you those, I'm going to present a few concepts to you. So this is where we're going to get a little technical for some things that images that I want you to have in your mind as we go forward. The first concept, and I kind of mentioned this with the Burning Man case, is the idea of a plume and a crosswind. So wildfire produces a plume through this injection of heat into the atmosphere. And if it's exposed to a strong crosswind in the environment, that plume will kind of form this arcing shape that moves in the downwind direction. So the plume is coming in here and then getting bent over in the winds. And we know from laboratory experiments that when a plume does this, it actually develops a number of different kinds of rotations in it. And 2 really important ones are something called the counter-rotating vortex pair. So you can kind of see that here. So on this flank, we'd have a rotation going this way, and on this flank, a rotation going this way. So that's counter rotation, kind of like a pitching machine, if you've ever played Little League. And then also these wake-like vortices that hang off of the underside of the plume and move downwind. And these tend to have alternating senses of rotation and kind of shed from the fire or shed from the plume and move downwind. And there's some images from the lab experiments that led to this kind of conceptual model here. So that's one concept that I want you to keep in mind. The next is just the idea of kind of what a plume or a jet does to some incoming airflow. So over here on the right, we could picture kind of a slice at the bottom here as wind is coming in from the left. What we'd have is a jet right here in the middle, and it's going to force, kind of like an obstacle, like a rock in a river, it's going to force the flow to split around it, actually accelerate around its edges, and then it will form a wake downstream of it where the flow goes in the opposite direction, right? So this blue area here, that air is actually going backward against the mean flow that's coming in from the left. And in certain situations, you can also break the symmetry of that and get some more complex flow patterns. So that's another one that I would like you to just kind of keep that image in your mind when we look at these, some of the data in the next few slides. Maybe. Okay. Okay, so let's look at this Loyalton Fire. And what we can do is we can take the radar data and produce what I'll call a time height diagram. So time is increasing along this axis. So this is early afternoon out to late afternoon. And altitude in meters is on this axis. And what we can see here is that this fire, the top of the plume, shown by kind of the black line here, goes through rapid growth. Goes from about 6 kilometers to about 13, maybe almost 14 kilometers in altitude out here. And it has these cores of very high reflectivity air. We saw that in the animation. This is all that ash and debris getting lofted in the updrafts. Down here on the bottom, I have what we'll call the rotational wind speeds. So these are from the radar, those couplets of inbound and outbound motion that show us the strength of a vortex. And the peak values in here, we can actually see we have a long duration, more than an hour-long period with strong vortices forming during this fire. And the peak magnitudes here are around 50 knots of rotational wind. And that's actually equivalent to something that's probably around an EF2 strength tornado when we look at ordinary tornadoes. And what we're going to do is we're going to kind of look at some of these periods in here and try to understand what's going on with these vortices. And the first way we'll do that is look at a time lapse from a webcam. This is looking back into the fire, so the wind is actually kind of in your face here, blowing straight at you. Let's go ahead and put this in motion and just let you get some sense for what's going on. If you look carefully, we can see that this side of the fire is rotating in an anticyclonic sense, and over here there's a weaker but still present cyclonic rotation. So this is that counter rotation. And then if we watch the right edge of the fire, which has stronger combustion, right around now, it's going to start to contract laterally and form suddenly a very strong rotation that is leading to these peaks in rotational wind speeds in here around 50 knots. And they actually went out and did a damage survey in this area and found large diameter trees snapped off in this strong anticyclonic vortex right over here. I'm going to call that an embedded vortex because it's embedded in the updraft of the fire, right? It's kind of co-located with that dense ash and smoke. If we look at a radar snapshot of that vortex, what we can see is the classic vortex signature. So there's a couplet, the green colors show flow toward the radar, which is off to the right here, and then flow back in this direction. So there's an anticyclonic circulation. That camera angle is looking into the fire from right here. We can also see some flow splitting, the green flow there, the green flow there, and then this larger region of red flow back into the fire. So that's flow splitting and a pocket of flow reversal, something like that, right downstream of the head fire. Okay, so that's a lot like the obstacle, the barrier, and the flow diagram that I showed you earlier. Interestingly, later we get a different vortex to form in this fire. So this is a weaker vortex. It's out here around 2200 UTC. And here's a pretty spectacular photo of this. And this is what I'm going to call a shedding vortex. It's downwind of the fire. It is actually separated from the head fire, which is back behind here. There may not even be flames in the base of this anymore. And it's much more rope-like and extending down from the fire. And I'm going to call this a shedding vortex, which we also saw in those diagrams previously. It also has a very strong rotational wind signature with it. So again, this couplet of outbound or inbound and outbound motion. And there's still some of those flow splitting characteristics apparent at this time. So to try to understand this in a kind of plume context, like these diagrams, we can take a radar volume and look at the location of all the vortices that we observed. Those are the black lines. And the shaded colors show the plume core as it arcs up and then back down in the downwind direction. Let me just kind of reverse that image so that it looks kind of like this diagram up here. So what we're seeing here is the plume bent over in the wind, and we're seeing vortex cores both embedded in the updraft. Those are my embedded vortices. And then these vortices that trail out underneath here and stay attached to the base edge of the plume. These are these wake-like or shedding vortices. And we can even kind of take those apart into different time steps. Just the embedded vortices, those were occurring earlier in the fire. They're all in the updraft cores. And then later, the shedding vortices that also start in the updraft, but then progress on down and out of the updraft with time. An interesting thing to note is that most of these vortices actually are extending up into the cloud base for this particular fire. So there's a clear link between that overlying pyro-CB and the rotation at the surface. We can kind of put that in the context of these diagrams, and let me just kind of show you the similarities here. So here's the jet core in a laboratory experiment, the flow splitting, flow reversal, and a curved wake region. In our case, the Loyalton Fire, the left image shows radar reflectivity. That oval is essentially the updraft or from the head fire. The dashed line shows the curved wake region. Over here on the right, I have the flow splitting around the head fire, the flow reversal. And if we track those vortex locations, they're all on the anticyclonic flank here, as well as along the anticyclonic shear zone. It's really quite compelling similarity, I would say, to some of the things that we know from the laboratory. 2020 didn't stop there. I'm going to move through some of these other cases a little more quickly in the interest of time and getting to all of your questions. We had another fire, the Creek Fire, which occurred near Huntington Lake and Shaver Lake, California. A really beautiful area if you've ever been down there, along the San Joaquin River Valley. And this produced what is arguably to date the largest or deepest pyro-CB in the United States. It was probably recently surpassed by some of those fires in British Columbia for the largest in North America. What we're looking at here is, again, a radar animation showing the evolution of the plume as it marches up the San Joaquin River Valley, and some extreme plume depths, which I'll show you, reached as high as 17 kilometers or about 55,000 feet. So thinking back to that poll question, this is going to be kind of our upper end event here, where these cloud tops are able to reach about 55,000 feet, which is truly remarkable. We're going to look at some similar diagrams that we had for the Loyalton case study. So here's this radar time height diagram. This is a very long-lived, high-impact fire. We can once again see rapid plume growth, in this case up to about 17 kilometers. So here's our peak plume depths. Very long duration periods with strong rotational winds, including rotational winds. I've actually updated these in a more recent analysis that exceeds 60 knots, which could be up in that EF3 kind of territory, like the Car Fire. This Pyro-CB actually produced lightning and downdrafts for a prolonged period of almost 12 hours, impacting the fire. It went through a second growth phase overnight and produced another set of vortices out here. So all these peaks and these dots down here, up around 40 or higher knots, would be what I would consider tornado strength vortices here. Those vortices were kind of continuous along the surface, marching from the south kind of to the northwest up through the terrain. And some of the higher impact vortices were near this reservoir right here, which is called Mammoth Pool Reservoir. And if you followed the news on this, a whole bunch of people got trapped here during this event because these vortices went right across the access road to the reservoir. Eventually this required helicopter nighttime rescues to get people out of harm's way. Let's look at these vortices inside of the plume and see where they're occurring. These are all anticyclonic, and they're occurring in what I'll call a bifurcating plume. So this plume has two distinct plume cores. You can see them right there. The anticyclonic one is the one where these vortices are forming. So this is one of the first strong vortices with rotational winds up to about 62 knots. Here's what the radar signature looks like there. We see some very similar flow patterns. We see flow splitting around the flanks of the plume, a pocket of flow reversal, and the vortex sits right along the anticyclonic flank here. The same thing later. This is another set of vortices that formed later. Once again, a splitting plume with kind of 2 plume cores, but all of the strong vortices in this case, once again, in the anticyclonic plume core. These ones weren't quite as deep as in altitude, but they were almost as strong as those earlier ones. Looking at the radar signatures here, again, we see flow splitting, flow reversal, and a curved ashfall region downstream of the head fire. Vortex 3, this is one that actually occurred at night. This one's a little bit different. It's embedded in a very deep upright updraft. The plume splitting doesn't seem to be as clear in this case, but we produce something that looks quite a bit like a hook echo in a conventional tornado, where the tornado is essentially right here, and here's this kind of curved ashfall region extending off of it, and you can see this clear anticyclonic couplet in the velocity field here. All right, one last case before I'll kind of start wrapping some of this stuff up. This was the Bear Fire, another huge fire in 2020. This went on to become one of the largest, most rapidly growing fires in California history. Fortunately, not quite as high impact as the Camp Fire, which occurred in a very similar area. There were kind of fewer developments in the way of this fire, but it moved equally as rapidly. So once again, we're looking at a radar animation of the evolution of the fire's plume. You actually see it change direction and then produce some really deep plumes later in its evolution. But the period of vortex generation is pictured here, where we get this deep fire-generated cloud being generated right here. Here's the radar snapshot corresponding to that very deep updraft here. We actually have very, very strong surface winds in this case, almost 50-mile-an-hour winds entering this photo from the left, sweeping through the fire and then launching vertically through the updraft here. Let's see, there we go. What's interesting about this case is that we get something that I'll call transient or shedding vortices. I'm not going to go into as much detail in this case, but these vortices were much shorter lived than the vortices on either the Loyalton or the Creek Fire, persisting for only about 30 minutes each. They formed in a similar region of the fire, the left front or anticyclonic flank of the head fire, but then are swept downstream quite rapidly and don't get as deep. But they occur in almost exactly the same spot as that they're occurring in the previous fires. We once again have flow splitting around the head fire, which is right here, a very strong pocket of flow reversal, producing a strong anticyclonic shear zone right here. And if you look at individual timeframes, the vortices just kind of march their way along that anticyclonic shear zone. So this kind of strip of high wind shear is acting as a source location for them. This fire also produces this curved ashfall region, and I'll get back to that in a few minutes. Actually, I'll get back to it right now. All right, so what's really interesting about this from a forecasting perspective, one of the things we're interested in doing with these is being able to identify what fires and when fires might generate these sort of tornado strength vortices that pose profound threat to firefighters, to the public, and certainly to property. And in all of these cases, we have very similar flow patterns. And I've actually added another case in here, another fire, the King Fire, and I've kind of annotated them, and they're all going in different directions, but if you kind of rotate your head around, what you realize, they all have the same sort of wind profile that changes from wind flowing in one direction near the surface and then experiencing a counterclockwise rotation, something that we call backing with height in the atmosphere. And that backing with height is setting up for that curvature of the ashfall region, which is that black curved line coming off of the fire. And it appears to be favoring one flank of the fire over the other for generating these long-lived high-impact vortices. And so it's not a mistake that all of these fires are producing anticyclonic vortices when they're forming in a similar kind of wind environment. And what I've added is another case in here, the King Fire, that has no wind shear in the environment. And so the ashfall region extends immediately downstream of the fire, and it's a much more symmetric setup. And it appears, at least in our limited sample size here, that fire produces similar flow characteristics, but never produces these long-lived high-impact vortices. And so we're thinking more and more that the anticyclonic preference is coming from the environment, from the wind shear profiles here. But that's kind of a hypothesis that we still need to fully flesh out. And one of the ways that we can do that is using really high resolution numerical simulations to look at the development of wildfire convections. So these are some simulations that a student of mine, Matt Roberts, is running with a high resolution large eddy simulation, where we can look at kind of idealized wildfire type scenarios to simulate and understand what it is about the environment that's giving rise to these anticyclonic vortices. And indeed, if we rotate the winds in the other direction, can we get cyclonic vortices to form out of these? And this is kind of similar to what we look at for ordinary severe weather, where the wind shear profile is very important in dictating what kind of storm development, what kind of storm motion, and what kind of tornado potential might emerge from that environment. So I'm kind of nearing the end here, but I just want to tease one of the things. So all of the data that I've shown you so far comes from fixed site radars, the NEXRAD weather observing network. But really where the cutting edge is for us now is using these deployable instrumentation, these deployable radars and lidars to go out to large wildfires. And this is a case actually from a very large prescribed fire in Utah that developed strong, once again, anticyclonic rotation, which you can see in this time lapse here. And we've had some opportunities to put a whole suite of instrumentation, multiple scanning lidars and a scanning radar out on this particular fire and observe in much, much higher resolution, you know, like a few meters every second instead of hundreds of meters every 10 minutes, the detailed dynamics of what's going on inside of some of these systems. And in this case, we're able to make some very high resolution kind of renderings of the rotation. So here the blues and reds are showing rotation in this column from LiDAR data, make estimates of the strength of rotation. And hopefully with the radar data that we now have coming online, we're going to be able to say a lot more about the origins, the initial location of the development of the vortices in these events, and also look at things like how strong the updrafts are, how strong the downdrafts are inside these really dynamic weather systems. So it's really a frontier of science for us right now, and thus it's a really exciting place to be working because there aren't a lot of answers, and there's a lot of work to be done, which means you can ask relatively simple questions and still do some really interesting science. Okay, so this is my last slide. So what I've shown you here today is that radars and lidars allow us to probe the internal, what I call kinematic, meaning airflow dynamics of wildfire plumes. And that opens up the possibility of understanding what's going on inside of these fire-generated extreme weather systems. We've seen just in the examples that I've shown you that we have multiple pathways to rotation and vortex intensification. We've seen 3 cases of plumes in a crosswind leading to anticyclonic vortices, both embedded within and shedding from the fire. The case that I was just showing that didn't go into detail with the research instrumentation, there's some kind of fire line geometry and plume-plume interactions going on in there. And then in the case of the car fire, we also saw that an ambient pre-existing shear zone can give rise to one of these vortices in the same way that a non-mesocyclonic tornado forms. And common to all of these, though, common to all the tornado strength cases that we have, is the co-occurrence of pyro-CB, of these deep fire-triggered thunderstorms aloft. And that's really adding this stretching dynamic to these plumes that wouldn't be there without those. And so really part of the formula or recipe to get these things to form. Although there are some feedbacks and lead lag relationships in there that we really need to further understand. So with that, my contact information is here on the bottom, my UNR email address, and always happy to field questions by email. And, you know, we actually have a lot already going on this year with, we've had 2 or 3 more cases with what look like tornado strength vortices already in the Western United States. You know, it's only mid-July, usually right around now that fire season starts picking up. and we're already in full swing. So it's kind of hold on to your hats, and hopefully things don't get too bad. So with that, Brian, that's what I have. Thank you everybody for your attention, and I'll turn it over to you, Brian, to moderate questions.
Excellent. Well, thank you, Neil, so much. That was, I mean, just wow. There's a lot to take in, certainly from what you shared, but clearly, as you mentioned, there's a lot left to be learned here, and just some really fascinating things that you shared relative to basically these weather systems interacting with the ground and wildfire. We have a lot of great, really thoughtful questions already, and if you have questions that you'd like to ask of Neil, our speaker this evening, make sure if you're on Zoom, use the Q&A button down at the bottom of your toolbar to submit your questions there, and we'll try and get to as many as possible. Really, actually, this is a question back early on in your slides when you're sharing about the wildfire-generated vortices, and you're showing a nice panel of the different ones. I had the same thought as well, an anonymous person as asking, what was panel D that you shared? It kind of looked like a luminescent jellyfish, and I kind of had the same thought on that.
That is a really good question. Hold on, let me
Kind of had like a bluish, like kind of like a one of those little like spin top kind of look to it.
see if I can. This is way back in the beginning.
Oh yeah, this is probably like slide 3 or 4, but it was. So you may have a ways to go on that, and I'll continue to look through some other
Oh,
questions.
okay. I
Yeah,
got
there
it.
we go.
Okay. Yeah. Okay. Yeah. So this is something you would not see in nature. So this is from a review article looking at different kinds of fire worlds that develop in different environments, and this is a sort of vortex ring and instability that can form under certain kind of laboratory conditions, but not particularly relevant to real world wildfires. So, maybe you could get this on your Bunsen burner in chemistry class, but probably not out on a fire. And I forget that there is some special name for this. It's called the blue whirl or something like that. But yes, it does look like a luminescent jellyfish. I agree. I think that is an excellent description.
Yeah, well, I like the blue whirl too. I think that's a great name. Another question from an anonymous attendee. I mean, you kind of referenced this a little bit, and it's amazing, unfortunately, how recent a lot of your examples are from recent wildfires out in the West. But I mean, are you finding that you're just overwhelmed by the new data and data examples and case studies that you have to examine?
Yeah, absolutely. We kind of need a small army right now to keep up with both the media interest in all of this stuff, and find time to really sink our teeth into it to answer these questions. And I've actually tried to. It's kind of a problem from a research perspective. It's like I kind of have to put on the blinders right now and not engage with some of the newer cases already from this year, so that we can really give a sufficient treatment to some of these earlier cases. And but they are useful, and they provide context to test hypotheses that we might have about exactly why, when, and where these are forming. And like most science, usually the more you learn, the more you don't know. You think you've got something kind of pinned down, and then the next case comes along and throws some curveball at you. So we have some rather complex ones already this year.
Yeah, well, that sounds like if there are any budding researchers out there, I think Neil could use your help. Question here from David. It's a little bit outside of some of the material you spoke on tonight, but David's asking about, so he says, I understand there's smoke from Russian wildfires that are mixing with smoke perhaps from fires in Alaska. He's asking about any just general thoughts on the environmental impact from that activity. And I guess sort of more generally, it kind of got me curious. I mean, you're talking about some pretty site-specific phenomena here, and these vortices happening in a given location. But I mean, obviously, this smoke does travel and even mix with, I guess, other wildfires as well. What are some of the impacts around that, if any, that you can speak to?
Yeah, exactly. I mean, I think you're right. The vortices are very local phenomena, but we have kind of hemispheric scale smoke transport that occurs in these fires. And actually, one of the things these really deep pyro clouds do is they inject that smoke very deep into the atmosphere, sometimes even into the stratosphere. And when it's there, it has a long residence time and can travel and stay there for 12 or more months. And so there's a whole research group that tracks the kind of evolution of these smoke plumes. And they have a scope similar to large volcanic eruptions and the total amount of carbon being put into the atmosphere. Obviously, smoke at ground level has lots of deleterious health impacts. Smoke aloft doesn't necessarily have those bad health impacts, but it does have climate impacts in terms of the way it interacts with sunlight coming into Earth's climate system. And so different kinds of smoke either reflect or absorb different fractions of that solar radiation and can lead to actually modifications of the airflow. I think this, as the scale of these fires increases year after year, it's becoming more and more of a big research question of kind of how big is this in the kind of global picture of the carbon cycle, of impacts on atmospheric circulation. And so, yeah, it's and certainly those Russian fires, the high latitude fires, burn for months and there's no suppression work, and there's thousands of them. So that's really where the bulk of that smoke is probably coming from.
Yeah, and even I guess as you're sort of referencing, even dropping dust particles and whatever onto glaciers, ice caps, etc., that kind of further accelerates some of that warming up there.
Exactly.
Well, all right. So let's go back to a somewhat simpler question that honestly would be great for you to clarify again, because you've made a lot of comparisons between sort of the ordinary tornado, or just tornadoes as we sort of the general public knows them, and pyro tornadoes. How would you sort of simply and quickly describe sort of the similarities and differences between the two?
Yeah, so ordinary tornadoes, most of that stretching action that's giving us this vortex is coming just from the energy release inside of a cloud, right? So an ordinary thunderstorm, it's the water vapor condensing into liquid water, then freezing into ice. That's where the energy driving the updraft and leading to the tornado is coming from, and interacts with the environmental wind shear. In the wildfire case, that same thing is happening, but it also has the wildfire heat that's driving the updrafts as well. And thus we get these really, really strong updrafts, these 130-mile-an-hour updrafts. So it's kind of like additive to the ordinary tornado process. There's this other process happening on top of it, which can lead to vortices at all sorts of different scales as well. But so yeah, I think they're additive. It's the same underlying dynamics going into a thunderstorm generated tornado are still at play here. Plus, it's kind of with the fire heat.
So this is kind of my own curiosity that I think you just piqued. I mean, I know you mentioned specifically some of these wind speeds that you've measured, and some of the examples you shared were around 140 miles an hour or greater. Some of the strongest, F5 plus sort of tornadoes can be, I guess, radar has indicated 300 plus miles an hour in some of these storms. Do you believe that? You may not have any evidence toward this, but I mean, what's your intuition tell you about? Do you think fire generated tornadoes could reach potentially that intensity under the right conditions?
Yeah, I think it's kind of unlikely. As important as the fire is in these really big kind of EF5 tornadoes, the amount of water in the environment that's condensing and then adding heat into the cloud is actually so much larger. These are very moist environments. Wildfires are very dry environments. And so even though the fire generated updrafts are really strong, it's hard to sustain the really, really strong convection that we get inside of like a supercell storm. And then the particular wind profiles that go into the generation of supercell storms, these really curved kind of wind shear profiles, probably a little less conducive to the kind of stationary. That's another issue. It's kind of like the wildfire is stationary, right? It's this fixed kind of forcing from the ground, whereas that storm can kind of continue to evolve in the downwind direction if it's not anchored to something. So I think it's unlikely, but I wouldn't rule it out. I mean, I think a big enough fire, the right setting, it is conceivable that you could see those kind of winds in that EF5 territory. But let's hope we don't get there.
Yeah, no kidding, because obviously there are lots of other impacts already associated with these fires. Sort of relatedly and great. I know there are a few different questions sort of in this area. Karen asked some questions about sort of, and you kind of hinted at this, the kind of the life cycle of these pyro CBs, and there are some other questions. So how often are they generating lightning? Is there actually precipitation falling? Are they actually traveling? You kind of said they're typically, a little more stationary, at least compared to other CBs. What is
Yeah.
kind of that life cycle like in a lot of these CBs?
Yeah. I mean, a few things. So one of the weird things, they're actually very inefficient at producing rainfall. They are so polluted. There's so much very small aerosol smoke being put into the cloud, and larger debris as well, that they make very, very small cloud droplets inside of these clouds. They're kind of the poster child for what we would call a polluted cloud, which are populated by tiny, tiny droplets as opposed to bigger droplets. And thus they're actually very inefficient at producing precipitation. But they can still produce enough large kind of ice particles aloft that they can generate this lightning in some rainfall, although very often that rainfall evaporates before it reaches to the surface. And you can literally see this in the radar data. You can see this pocket where it's producing rain, and you go down to some lower elevation scans and there's nothing there. And that can produce these dangerous downdrafts in that environment as well. As far as the life cycle, we get a wide range here, and the environment matters a lot, but sometimes they're quite pulsy, where we'll get kind of like a puff and it goes quite deep, but then the top of the cloud will be sheared off and propagate downstream, and then it will pulse again, and it will do that over and over again. But for the right environment, we can get sustained kind of upright convection, like during the Creek Fire, during these recent events in British Columbia. And Australia is really good at producing these as well, the kind of longer lived ones that can produce a lot of lightning and then go on to start a lot more fires. And so more often than not, the lightning, the lightning is a problem. The precipitation is almost never enough to suppress the fire activity. Occasionally, if it's a moist enough environment, you can get that. But more often than not, they're a hindrance, not a help to the fire ground.
Yeah, so definitely some differences to the supercell cumulonimbus that we might be thinking of and all that, and certainly a dry environment. If these are big enough fires to begin with, it's probably pretty dry out. Let's see, a number of really great questions here. Thanks everyone for sticking around and submitting questions. I guess Neil, put your geoengineering hat on just for a second. Do you think there may be any way that you could alter the force or the direction of a fire if you disturbed some of these vortices?
Boy, I think having watched these fires and watched them try to do things like, with the biggest tools that we have available to alter the direction of travel of these fires, I think it's really an intractable problem from that perspective. You'll watch these 747 sized tankers putting down millions of dollars of retardant, and then just watch the fire just chew straight through that, or just loft embers straight across it. It's hard to imagine what you could do to alter the environment sufficiently surrounding the fire while it's happening to alter that outcome on these big days. These big days are just, get out of the way sort of days. And really the energy should be spent instead in fuels reduction and fire resiliency and all the antecedent stuff that goes into, kind of making our communities more resilient to fire or less prone to fire in the first place. Once we're at Pyro CB and Pyro Vortex, kind of forget about it. It's off the charts at that point. You've already lost at least that day, I would say. And then, of course, I'd be remiss to not say, the single best thing that we could probably do would be to stop dumping so much carbon dioxide into the atmosphere, because we're seeing a rapidly changing fire environment in the Western United States and in the Arctic or high latitudes in any case, and also in Australia. And the fewer opportunities, the better. So that would be my plug for geoengineering would come from the reducing the inputs to the system.
Yes, yeah, some of that preventative health that healthcare that we should be doing for the planet. I hear that. Um, a lot of questions. There are a number of questions around predictability and modeling. Some of the things that you spoke to, and really clearly on the cutting edge here. And I guess uh, let's see. So here's a great question from Laurel. She asks, in terms of using this modeling to predict whether a fire will create tornadoes, is there something that people will be able to do in real time if they're combating a fire? Is it only possible to predict through radar and lidar? And I guess sort of I'll add on to that, for the general public, is there some sort of uh, what's the forecasting and communication like around, some of the prediction? Because I don't know if National Weather Service has a pyro tornado watch or warning, product or something like
They're
that.
working on it, and the incident meteorologist is kind of the National Weather Service now actually they issued a fire tornado warning for the Loyalton case that I showed the Weather Service office in Reno. But yeah, so I mean, these are basically what I've presented is basically kind of like nowcasting tools, right? We can use radar data in real time to identify some of these flow signatures as they develop. One of the early warnings is that flow splitting, flow reversal signature. When you start seeing that, the fire is modifying its environment sufficiently that it could start producing these sort of things. Doesn't mean it will produce these, but it could. So that's kind of the maybe that watch sort of level. The warning is similar to tornado warnings where, there is a tornado now, and it is still useful in terms of being able to pull resources off of fire lines and identify that there's a extremely hazardous situation evolving in this moment. But we're not at that, tomorrow there's going to be, high potential for fire vortices on these fires, but there is a weather model coupled with a fire spread model called Wharf Fire. Now, some of you may know this. There's this model called the Wharf Model that's actually the backbone of our kind of short-term forecasting infrastructure in the United States. And it has a two-way coupling with the fire spread model. And these are now starting to be run in real time, where when we have a new fire ignition, you can put the fire into the model and get some crude fire evolution and interaction with the atmosphere and feedbacks, and produce things like PyroCBs in the models. They still can't do things like produce the vortices. Those are occurring at smaller scales than we could, like a herd can't forecast, for example, tornadoes. It can forecast environments conducive to tornadoes. So those tools are going to be coming online in the next, kind of 5 years. But we have a long way to go. I mean, the fire modeling part of this is really challenging, and but hopefully some of these nowcasting tools can kind of be in the pipeline sooner, and at least give us that, this is happening now perspective, which is a little bit useful.
Yeah, I'm sure there are lots of folks, if fire's nearby, they're at least aware, but that may be another tool just to kind of help get them, if they have their go bag ready or whatever, give them that extra time to get out of harm's way, I suppose. Well, there are so many fantastic questions. Unfortunately, I think I'll just ask one more for um, this evening. I guess just kind of wrap together a few different questions. And Neil, if you can share that last slide again of yours, just so folks have your contact information. And for any questions we don't get to this evening, you can also try and send them over to education@mountwashington.org. Certainly, we'll make sure that pass these along to Neil as well. You can see his email down there at the bottom of the slides. I guess so. We touched on a little bit about you touched on a little bit about climate change related to fire, and certainly you've been speaking quite a bit about case examples in the Western United States where you are, and certainly where the major impacts, fire impacts, are happening in the US. Sort of more generally, I mean, this might be a simple question, but I mean, what percentage of these major fires are happening in the Western US? And sort of opposite to that, most of the audience joining with you tonight, in the Northeast, what should people in the Northeast be thinking about in terms of wildfires for the future?
Yeah. That most, there's a heavy focus on the Western United States. Obviously, we have a kind of full-fledged fire season that lasts for many months. in some ways it's a year-round fire season in places, and so our opportunity to experience these high impact fires is is almost always going to be higher than it is along the East Coast. That said, when you look historically at the Northeast, even going back to the creation of the Forest Service around the logging impacts in the Northeast, I'd encourage you to Google, I think it was called the Owl's Head Fire, which was, not too far from Mount Washington over in the Pemigewasset Wilderness. And there's some pretty compelling photographs of extreme pyrocumulonimbus being generated by fires there in New Hampshire. And to me, that was kind of a wake up to think about, anywhere that we have large fuel loads, when the conditions are right, we can get big fires. And the upper Midwest is another place that historically we've seen some of these, including in the historical record, some enormous fire generated vortices that devastated whole towns. We've seen recently some very high impact fires down in the Southeast in Tennessee, in the Great Smoky Mountains. And Florida and Georgia have very fire prone parts of the year as well. And so actually, unfortunately, increasingly, I think this is going to be, we're going to see more high impact fires in the decades to come in some of these environments. But yeah, still fire, I live in fire country, and it's kind of this, you get this tingly feeling on some of these days when you walk outside here that, these are kind of watch out days, and it's a profound problem here for sure.
Well, thank you, Neil. I'm sorry to end on such a sort of somber note there, but certainly I know I really appreciate, and I'm sure folks here really appreciate the work that you're doing and the impact that it can have on our communities. Thank you for your time that you've given this evening for presenting. Really fantastic stuff this evening. For the rest of you, for folks, if you enjoyed tonight's program, sincerely ask that you consider becoming a member of the Observatory if you're not already one. Consider donating to help support programs like these over at mountwashington.org. There'll be a survey that follows up after this program as well. If you have thoughts about tonight's program, any suggestions about future programs or topics. So thank you in advance for those of you who will fill that out. Don't forget to join us for our next program next month. It'll be Tuesday, Tuesday, August 10th. And that's when New Hampshire State climatologist and UNH Associate Professor Dr. Mary Stampone, as well as observatory staff and interns, will discuss the newly released 30-year climate normals and how they've changed on Mount Washington and also within the state and region. So don't forget to register for those programs over at mountwashington.org/SITM. And I hope you all have a great night. Hope to see a number of you over at Seek the Peak this weekend on Saturday. Thanks again, Neil. Have a wonderful evening yourself, or at least the rest of the afternoon there. And hope to stay in touch. Take care, everyone. Have a great night.
Thanks, everybody.